Hello everybody, I'd like to talk about the photoelectric effect. It's an interesting phenomenon in physics in which when you shine light or any form of electromagnetic radiation on a conductor, an electric current may be produced. Um, Albert Einstein won the Nobel Prize in 1921 for his work on this. And the nice thing is it's fairly simple to understand. So let's imagine here in the orange here we have some electromagnetic radiation. It can be visible light, it can be X-rays, it can be gamma rays, microwaves, radio waves. These things are made up of photons, so there's these tiny little photons. Now this is what made, this was the hypothesis that Einstein, well not, I mean there were already physicists at the time that were making these hypotheses that energy comes in these little packets called quanta. And in the context of light or electromagnetic radiation, we call it photons. So these little photons are traveling through this array of light, and as it's incident on this metal, let's say this is some metal, it can be, doesn't have to be a metal, just any conductor or semiconductor or something. And then what happens effectively is that these photons might eject or emit an electron. So you can imagine a photon colliding with an electron, and then it shoots the electron out. Now, of course, in a sophisticated setup, this piece here could be like a circuit or something, and then this flow of electrons, is what we call a current. So flow of electrons is electric current. It's an electric current or electricity. And there's some interesting aspects of this. So the thing is, we have to first look at a wave. So let's analyze a wave in general. So let's just consider a wave here. So if you have a wave, sinusoidal wave, something like this, you can think of trigonometry or anyway, so some properties of the wave. Let me just draw a imaginary line there. So the highest point of the wave, these pieces here, this is where the wave reaches its highest point, the peak. This is called the crest of the wave. So probably just write it down. Highest point, or points, highest point of wave, and this is known as the crest. And then the lowest point of the wave, which will be these guys here at the bottom, this is when the wave reaches its absolute minimum. So the lowest point of the wave, this is known as a trough. Now the wavelength is the distance between successive crests or troughs. So we use the symbol lambda, the Greek letter lambda, for the wavelength. And then something else that we want to know about with regards to waves is so we spoke on wavelength. Now there's also the wave height. So this is the distance between the highest point and the lowest point. And in general, half of that is the amplitude. So the amplitude, so let me write this here somewhere. The amplitude of a wave is effectively from the midpoint. This is why I drew this this dotted line. It's the distance from the midpoint to the top or the bottom of the wave. So it's basically half of let's say the crest minus the trough. Now of course it's not always exactly a half. depending on the wave might not be as regular as this. It could be a dampening wave where the wave is getting smaller or higher again, and so on and so on. So anyway, it's just basically it's better to think of it as the equilibrium point. So the distance from the equilibrium point of the wave to the highest or the lowest part. The amplitude is the amount of energy transferred by the wave. Now the thing is, at the time when all this research was being done back in the late 1800s, early 1900s, there were a few things here that were not making sense. For example, the intensity, and I won't give a formula for the intensity, but the intensity of a wave is proportional to the amplitude squared. So the greater the amplitude of the wave, the more intense the wave will be. So effectively, a lot more energy is being transferred within, per unit time, if we can say so. So if you're shining some light on a surface, the greater the intensity, the more light is being shown onto the surface. But what was noticed in with this photoelectric effect is that, if we go back to this diagram here, is that even if you what they noticed is that if you increase the intensity, so if we had to increase the amplitude, let's say we had to make bigger, more intense light shining on, what was noticed is that the current would increase. This makes sense because the more intense the wave is, the more photons there are, and the more photons there are, the more electrons it will eject or emit. So it makes sense that the current would increase. But what did not make sense, and what was confusing, was that the energy of these emitted electrons was not increasing. So for example, now, if I can just change colors here, let's go back to a different color here, maybe gray or whatever. So if you've got your metal here, I don't think I'm going to change colors all the time. I mean, you got a whole lot of electrons. You would imagine that if photons of higher energy were coming in and ejecting or emitting these electrons, you'd expect the kinetic energy to be higher. This makes sense from a classical physics perspective. For example, if you took a ball with a certain amount of energy and you rolled it or kicked it or whatever at another ball, you would expect that when they collide, this ball will move off with quite a bit of energy. The more energy from the first ball, and then the more energy would go to the second ball. Obviously not the same amount, because some energy would be lost. But the point is, it makes sense. The harder you, for example, kick a ball, the further it will go. So it was a bit shocking to find that the kinetic energy of electrons stayed the same, or stays the same, irrespective of how intense the incident wave is. Okay, now this is obviously quite confusing, because so now let's see what's actually happening. Why is this happening? Well, it turns out that the metal itself has something called the work function. Now the work function, which is denoted by W or phi, the Greek letter phi, like that or like that. So all of these are equivalent. The work function is the energy that the metal has in keeping those electrons inside the metal. So in order for the electrons to stay inside here, there's a certain amount of energy that's keeping them here. And the amount of energy that keeps them here is dependent on the metal. So different metals will have a different work function. You can look up on a table and see copper and whatever, magnesium and zinc and so on. So the different metals will have different work functions. And the thing is, we can denote this work function as H. H is Planck's constant, and nu subscript 0. So some textbooks or books will use F for frequency. I'm going to use nu. So this is the Greek letter nu. It's like a curly V. And the thing is, in order for an electron to be emitted, the incident radiation must have an energy, or at least the photons, let's go E photon, which is H nu. I won't put the subscript now here, because we're dealing with different frequencies. It must, of course, be greater than the work function if we want an electron to be emitted. So if the incident radiation has energy less than the energy of the work function, then no electrons will be emitted. And this is also something that caused confusion, because in a classical understanding of physics, you would imagine that, let me try and draw, like you would imagine that as radiation is incident on the metal, there would be a sort of build-up, an accumulation of energy. So energy will build up, build up, build up. I don't know how to draw that, but you can just imagine that more and more energy is accumulating inside here, and then eventually there'll be enough to start ejecting the electrons. So this is what people were thinking about at the time. So eventually, like almost like heating up a surface. You heat it up to a certain point. Once it's hot enough, it will do something. So this is what was understood in the classical way. But what they were discovering is that no matter how long you shine the radiation or the light on the metal, it wasn't, electrons just wouldn't be emitted. And then alternatively, with certain other types of radiation, the electrons would be emitted instantly with no lag time. So this was quite puzzling, because at the time the molecular and atomic understanding of matter wasn't not generally accepted in the scientific community. Now I'd like to speak about a few constants, important constants and stuff that comes up. So H is Planck's constant, named after Max Planck. So this is Planck's constant. So the value for Planck's constant is 6.626 times 10 to the minus 34. So as you can see, this is a very, very small number, joules seconds. And because we're dealing with electrons and so on, sometimes we don't want to work in joules when speaking about energy. So we rather work with electron volts. So an electron volt, let me just explain it very quickly, is the amount of energy required for an electron to move across a potential difference of exactly 1 volt. So it's for this electron to get from here to here with a potential difference of 1 volt. and an electron volt, which is just denoted EV, the value in joules is 1.602 times 10 to the minus 19 joules. So as you can see, it's a very small number as well. So that is why in this context, these are very small numbers. So when you're dealing with atomic level stuff, we normally work with electron volts. So Planck's constant in electron volts is a little bit different. 4.136 times 10 to the minus 15. So instead of joules now, electron volts seconds. Now another thing I just want to mention as a reminder, when we dealt with waves, I mentioned it earlier. Okay, this is a badly drawn wave, but anyway, the distance between the crests, for example, is the wavelength, and the frequency of a wave tells us, let's say we had a point here, point A, and it tells us how many times within 1 second do crests pass through this point A. So as this wave is traveling, as it's traveling, how many times is it going to pass point A in 1 second? And that is why frequency, which is denoted F or nu, is measured in, let me just write measured in per second, or hertz. Hertz named after the physicist Heinrich Hertz. So hertz or seconds to the minus 1. So normally some of us prefer to write it as seconds to the minus 1 because it's in keeping with the SI units and it's easier to see things cancel and so on. But basically Planck's constant could be, instead of joules seconds, you could write it as joules per hertz. So I suppose it will depend on your preference or how you're examined. So, but I prefer to just use per second. So frequency is measured in per second, and of course we know that energy is Planck's constant times frequency. So the greater the frequency, the greater the energy. Now, taking all that into consideration, it's interesting to also notice that the work function, or you want to write it like that, or if you want to write it like that, is Planck's constant times the threshold frequency. And we can write this as, because frequency is the wavelength frequency is the speed of the wave, and the speed of the wave is c. Because we're dealing with electromagnetic radiation, the speed is always c divided by the wavelength. Now c is the speed of light, or the speed of electromagnetic radiation, which is approximately, I'll say approximately 300 million meters per second. So from the frequency you can calculate wavelength, and from wavelength you can calculate frequency. And in this case I'll put the subscript 0 here as well to say this is the cutoff or the threshold wavelength. Now often what happens is there's also this concept of stopping potential. Sometimes you'll hear them speak of stopping potential or stopping voltage. And this comes about from this idea of writing energy in terms of electron volts. So if you add the kinetic energy of your photon, of your electron, the kinetic energy of your electron um, K max, whatever you want to call it, we can write this as electron volt, and I'll put a small s there for stopping. So this is the stopping voltage. So it's effectively the same thing. The stopping potential or the stopping voltage is the same as the work function in the context of the photoelectric effect. So stopping voltage is the same as work function. So I just put all this out here in case there's, because different textbooks and stuff might use different terminology, and physics and engineering might have different ways of teaching these things. So as the photons come arriving with the energy, E photon, and as they become incident or touch onto the metal, these electrons inside here, which are held in place by the work function, the energy of the photon must be greater than, I suppose, greater than the work function plus the maximum energy of the electrons. So the electrons have their own kinetic energy. I mean, they're moving around and so on. So in order for this electron to be emitted, the energy of the photon must be greater than the work function, which is the energy that's holding those electrons in place, and the, let's say, greater than or equal to the maximum. And if we rearrange this, we get, let's make kinetic energy of the electron, of the emitted electron, the subject of the formula. This will be energy of photon. Now, of course, all the photons have the same energy with the same light, unless we have, let's assume it's monochromatic light, so it's the same light, and then minus the work function. And then this, of course, is just Planck's constant times the frequency of the light or the radiation minus Planck's constant and then the threshold frequency. And if you are given these numbers or this information, you can do some calculations. So I think we should do an example. That's a very straightforward example. So visible light of wavelength 530 nanometers is incident on a metallic surface whose work function is 1.50 electron volts. So that's quite tiny. I suppose we could draw a picture. So we've got visible light coming in here with a wavelength of 530 nanometers. And then we've got some metallic surface here which has a work function of 1.50 eV. What is the stopping potential of the metal? So before we even do that, let's just get our units right. So 530 nanometers is 530 times 10 to the minus 9 meters. And if we want to stick to the conventions of scientific notation, we need to shift this comma back, so it becomes 5.30 times 10 to the minus 7 meters. And then I think electron volts, we can just leave it like that, because I think we'll work in those units. So these emitted electrons are coming out with their kinetic energy. So from earlier we know that the energy of the photons, or the energy of the electromagnetic radiation, is equal to the kinetic energy of the emitted electrons plus the work function. Now this guy over here is the charge, electron, times the voltage, and it will be the stopping potential. So we're going to ultimately solve for stopping potential. So if we rearrange here, we know that the energy of the photon is Planck's constant times the frequency of the radiation is equal to the charge of the electron times the stopping potential plus. So let's rearrange and let's see what happens here. So I'm going to rearrange a bit. So the EVS is equal to Planck's constant h, and then times nu minus w. Now the thing is, we were given the wavelength, we weren't given the frequency. So we need to remember that the relationship between wavelength and frequency, it's an inverse relationship. So frequency is speed of light over wavelength. And if we substitute this, we end up with EVS is equal to hc over lambda, and then minus w. And then suppose we could start plugging in values here, I suppose. So let's do this. EVS is equal to, so h, we're going to use electron volts, yep. So Planck's constant in this case is 4.136 times 10 to the minus 15 electron volts seconds. And then this is of course multiplied by the speed of light, which is 3 times 10 to the 8 meters per second. And now all of this must be divided by the wavelength which we were given, which is 5.30 times 10 to the minus 7 meters, and then of course all this minus 1.50 electron volts. So I suppose we can plug this into a calculator, but before we do that, let's see what happens to the units. So the meters cancel, the seconds times second to the minus 1 cancels, so we left this electron volts here and electron volts here, so this is excellent. At least we didn't make a mistake with any of the formulae. So 2.34, let me use 2 decimal places. And then like we said, this is just electron volts. And then minus 1.50 electron volts. And I think this one is not too difficult. I think it's 0.84 electron volts. And of course we can cancel the charges on both sides. And therefore the stopping potential is 0.84 volts. So, and then question B says, what is the cutoff or threshold wavelength? So this is a straightforward answer here. This one is quite straightforward. Once again, we know that the relationship between frequency and wavelength is inverse, and the constant, of course, is the speed of light. So our work function, remember the threshold frequency is related to the work function, the metal that we're dealing with. We know this is 1.50 electron volts. And furthermore, we know that this is Planck's constant times the threshold frequency. So it's just a little bit of algebra, just a little bit of substitution here. And with some manipulation here, it's just hc over lambda subscript 0. And then a little bit of algebra, because we want to make lambda 0 the subject of the formula here, which is just hc over w. And then we just plug it in. So Planck's constant here is 4.136 times 10 to the minus 15 electron volts second, and then of course times the speed of light here, which is 3 times 10 to the 8 meters per second, and then this must all go over the work function, which is 1.50 electron volts. So the electron volts cancel, and then the second cancels with the second to the minus 1, so we're left with meters. So at least we know our formula is right. So now we just need to use the calculator properly. 0 point and then 5 zeros. So 0 points 1, 2, 3, 4, 5. 1, 2, 4 meters. Now of course we don't like this, so we want to shift this comma, and we shift it 1, 2, 3, 4, 5, 6 times. So we end up with 1.24 times 10 to the minus 6 meters, or you can write it as 1.24 micrometers.